Welcome to the 5th webinar in the 2025 Small Water Series webinar series. I apologize for the delay. We're having some technical issues with our regular moderator, so I am going to be here for the next little bit, and then hopefully we can switch over for the Q&A. My name is Natasha Scott, and I do technical support at on the Small Water Systems helpline. You may have emailed. If you ever email our info then you would be talking to me. Before we begin, I would like to acknowledge that Thompson Rivers University campuses are located on the traditional lands of Tk'emlúps-te-Secwépemc, Kamloops campus, and Telek, Williams Lake campus within the Secwépemc, the traditional unceded territory of the Secwépemc. Thompson Rivers University and its partners hosts an annual free webinar series and courses designed to provide technical information, resources, and tools to all small water system owners and operators, including Indigenous small water systems. These webinars, courses, and our website cover topics such as treatment, regulations, operations, maintenance, and water quality monitoring. The Online Help Center is committed to assisting small water systems across British Columbia in implementing multi-barrier approach to drinking water, ensuring that safe, potable drinking water for their communities is in compliance with government regulations. Our free webinars are scheduled every 2 months in 2025. If you are an EOCP certified operator, each webinar will count for 0.1 CEU towards your certification. Upon completion, participants will receive a certificate which can be submitted to the EOCP. You'll receive your certificate 24 hours after the end of today's webinar. We have an exciting update. We may have mentioned it before, but we have 2 free online courses. One is an exam prep course, which is a series of questions to help you drill and practice for your certification. And the other is an emergency response preparing course, which is a great background that every small water system operator should look into. Today's webinar is going to be a 1-hour presentation followed by a 30-minute Q&A session. We ask that if you have any questions, hold them till the end of the webinar. You can post them in the questions section and we will pick them up at the end of the webinar and give them to Bradley to answer. Today, we're going to talk about operations and maintenance of ultrafiltration membrane systems. This webinar will feature an overview of membrane filtration systems at the Rivershore Water Treatment Plant. This includes tackling unique operational issues such as pre-treatment, chemical and recovery cleans, clean in place, membrane integrity testing, and water quality monitoring. Our presenter today is Bradley Severin. Brad is a utility systems manager and senior operator at the Rivershore Utilities in Kamloops, British Columbia. He holds a certificate in water treatment level 2, wastewater multi-utility level 2, water distribution multi-utility level 1, and wastewater collections multi-utility level 1. And we are very happy to have Brad here to share his knowledge with us today. So I'm going to hand the presentation on to Brad.
Perfect, okay. Hello, everyone.
There you go.
Perfect, let me just get set up here. I think everyone can see my screen. Let me just see. Yes.
Looks good.
Hello. Perfect. Yeah, thank you, Natasha, for the introduction. I am Brad Severin, obviously. I am here to talk to you a little bit about the operation and maintenance of ultrafiltration membrane in small water systems, and give you a few insights into how we've tackled operations at Rivershore's water treatment facility. So to start off with, just a little bit about myself. I'm the utilities manager of Rivershore Estates and Golf Links, and the principal operator for all 4 of their EOCP certified facilities. And I serve as the principal operator. I'm there on a day-to-day basis. I graduated valedictorian from the TRU Water Treatment Technology program in 2022. Professionally, I have experience in both water and wastewater treatment. I did a co-op term at the new McLaughlin Point wastewater treatment plant built in Victoria in 2020. And my experience includes troubleshooting complex treatment systems, coordinating with regulators, directing managing students and other operators. I do take a student from the Thompson Rivers University water program every year as a summer co-op experience for them. I've worked with facilities that were struggling to meet compliance and help them achieve their environmental legislative goals. I have experience in non-potable reuse of wastewater, both at Rivershore and my previous experience, and I've gained on hands-on knowledge of membrane filtration applications, and I'm just really excited to be here. Thanks again, everybody, for attending. I'm looking forward to sharing my experiences and discussing membrane filtration operations and best practices, and I hope some of what I have to say is a valuable insight or might help you in your decision if you're commissioning or being involved in the commissioning of a new plant for your small community. And yeah, let's get started. So basically, over the next hour or so, I've got 3 goals. Number 1, provide a brief overview of the ultrafiltration process at Rivershore and kind of why we opted for that technology over others. I say we, but these decisions were made probably 15 years ago before my involvement. And I especially want to compare the chosen solution to some of the other competitors that were being considered at the time, just because what we ended up with actually ended up being a very effective system for what we required given our treatment goals. I also like to highlight some operational issues we've encountered when it relates to the membrane filtration aspect of our treatment. Obviously, if I sit here and discuss every problem that we've had, that we'd be here all day, but as any facility does, we encounter issues, and a big part of operating a small water system is finding innovative, cost-effective solutions to these problems that always present themselves no matter what you do. Finally, I'd like to share some lessons that I've learned and some of the best practices that I believe make ultrafiltration a solution worth considering for small water systems like ours. I encourage everyone to write down questions as they come up. Hopefully they do come up, and like Natasha said, we'll tackle them at the end during the 30-minute question period. So let's jump in just with a little bit of background. Obviously, you can see a bit of our site in that background slide there. Our treatment system and the site of the treatment system isn't pictured, but just off to the left, you could, if this point of view was a little bit wider, you could see where our intake point comes in to our intake sump. And then obviously, we have a lift station on shore. It's actually in the corner of the parking lot. What would you call it? The kind of the closest to the green, the 18th green there, where you can see people playing golf. Rivershore, obviously, is a golf course, but it is combined with a residential subdivision. It's located about 20 kilometers east of downtown Kamloops and about 12 kilometers southwest of Pritchard. The surrounding area is heavily developed with agricultural, recreational, and industrial activities. This means the source water itself is exposed to a variety of potential hazards. So, careful treatment and monitoring of raw water are an essential part of our process. The surface water intake is located within a 10-foot vault that I mentioned on the actual riverbed itself. And it's installed so that the water level in the river directly influences the water level in our low lift station, which is hydraulically connected to the intake sump through a high density polyethylene lateral that stretches all the way under the riverbed and into the intake sump and hydrostatically charges the low lift station, is what we call it, which ultimately supplies the treatment plant with its flow of raw water. Once treated, the water that is then entered into like a fed and supply distribution network and stored in ultimately a 655 cubic meter treated water storage reservoir. And that is connected to 200 different consumer homes, in addition to our commercial buildings like the pro shop and the restaurant. But for the plant itself, when designing Rivershore's water treatment system, the engineering firm responsible was focused on selecting a technology that would balance cost and performance. As you're probably all familiar, cost is a major factor in a lot of decisions made in small water systems, and it's one of the things that should be most considered above anything else. But we still wanted something with good pathogen removal. There was also a major concern over footprint and where this facility was going to be constructed, which given the limited footprint of the solution that we did pick, it ended up in the same maintenance yard that the golf maintenance crew ends up doing their operations out of. So we work kind of shoulder to shoulder in that way. Ultrafiltration was chosen because it's been proven to provide high degree of log removal for pathogens, specifically bacteria and protozoa, typically proven to be about 4 log. So that's 99.999%. It doesn't do such a great job with viruses just because they tend to be smaller than the pore size of the membrane, but that's what we have post-chlorination and other disinfection methods for. So choosing this model required careful consideration of multiple factors, as well as some negotiating with engineering firms. There was a couple of different offers being thrown around at the time, but the design chosen was ultimately a design by BI Pure Water, which is fairly prolific. Some of you might even be operating plants with their design, especially if you're in the northern part of BC. And the membrane module chosen was the XF55, which proved compliance with all regulatory requirements in British Columbia, had a relatively small footprint in comparison to its competitors. Kind of for an ultrafiltration membrane setup, it's fairly simple to operate. It doesn't have a waste reject line or a dedicated air blower system, which would require additional maintenance. Relatively easy to clean, which helps maintain performance and membrane life, especially compared to the main alternative being considered, which was the GE Z-Weed model, which was ultimately passed on due to basically footprint concerns as well as higher costs. For the process itself, we are, to get a better understanding of the treatment process, I think it's a bit helpful to gain just basically a bird's eye view understanding of the whole process. The flow chart on screen is basically just a very abstract kind of abbreviation level, but you can see it moves in a linear pattern all the way from basically our source water at the low lift station to the feed and supply distribution network to reservoir. We'll touch briefly on many of these steps as they're kind of crucial auxiliary treatment mechanisms in addition to the UF membranes. But yeah, we'll start from the beginning and just chat a little bit more about design. So yes, the design was intended to accomplish a few goals, and basically the council wanted water quality that either met or exceeded the water quality produced by the Kamloops Center for Water Quality, which in itself sounds a little bit ambitious, given the additional goal of maintaining a moderate cost. But there were a few factors that made it possible. We have a much lower flow, pressure, pumping costs, demands, chemical costs, and kind of everything in between. So given modern technology and especially ultrafiltration, they deemed it possible, and they were right. I think our treated product is very similar to what the city of Kamloops produces. The plant was designed to meet an estimated peak water demand, but in practice, and especially over the years, this peak demand was underestimated at the time. Many of our residents are heavy water users, going up many hundreds of percent during the summer irrigating months. It's important to note that the golf course irrigation system is separated from our drinking water, domestic water treatment system. But the residential irrigation system still, per household, still draws from the supply of potable water. So in 2010, the Strata Council began accepting bids from engineering firms for a new treatment plant. Their goal was to achieve similar water quality to City of Kamloops. The plant design was intended to replace the high lift station, which was basically where the low lift station would originally send water from, where it would be simply chlorinated and pumped up to the reservoir. But seasonally, we were dealing with high turbidity periods, which would end up in boil water advisories, same as City of Kamloops. Now, with the new design, the high lift station has basically been removed from the process, and the low lift station is what supplies flow and pressure to the water treatment itself through about a 1 kilometer drilled line from the riverbed to the treatment plant's location in the maintenance yard. Historically, that high lift station or the chlorination process was providing it wasn't providing a degree of treatment that would be considered acceptable today. I was looking back in old turbidity logs at customer taps, and I was seeing numbers as high as 22 NTU during freshet, which I don't think anyone would consider safe to consume. So obviously the need for an effective treatment process that could be relied on was considerable. So in their design, it needed to reflect a response to both regulatory expectations and to local operational challenges, including basically high seasonal demand during the summer, appropriate flow according to that, and the occasional turbid source water during freshet. On the right side of the slide, you can see the original P&ID drawing from 2010, 2011. It didn't turn out that great on the slide itself, but if you're looking back at it later, you might be able to zoom in and get more of the detail, but it shows kind of step by step the original process. But there are certain parts of this process that have been removed due to redundancy and other factors over time. But we'll start a bit on the intake side. And speaking of incoming turbidity, much of our operation does come down to seasonal source water quality and demand. The South Thompson is an extremely high quality water source, as those who operate any plant in on the South Thompson River know. It has only a very moderate concentration of soluble organics and a low average turbidity for a river source, and even during freshet, depending on the year. It provides a very stable raw water in terms of many parameters, including pH and measurable UVT and stuff like that. So that makes it easy to treat because you can always kind of know what to expect. Our intake, I described its location a little bit more. In 2023, we did end up in a situation during the fall winter months where the South Thompson reached a historic low in terms of its river level. I think the previous established low was in 1910. And the rock surrounding the intake enclosure had become blinded off with deposited silt and sediment, which provided an operational challenge. We were ripping our hair out trying to find ways to supply water to the intake sump, which would then supply our treatment plant ultimately. So it was a challenge initially to get it to keep up, and eventually it failed altogether. So we worked with Interior Health, Ministry of Environment, Kamloops Indian Band, and others to make sure that our work per our construction permit was done responsibly and according to legislation. And we swapped out all of the rock surrounding the intake and replaced it with new rock, which you can see hopefully on the slide, one pile versus the other. And that solved all of our flow issues, despite the continuing low level and the low level since, because this is a problem related to climate change that's unlikely to change. So we need to be thinking of innovative solutions, especially in the context of a small water system, to kind of address these problems. We'll move on to pretreatment. So in general, pretreatment is common when UF membranes are used, considering that the membranes are your most important asset monetarily, but also as your main treatment mechanism. So by removing suspended solids, colloids, and larger particulates, suspended silts, through physical filtration, through some kind of coagulation and flocculation process, chemical oxidation, you can use pretreatment to remove the risk of, not remove, but reduce the risk of fouling, abrasion of delicate hollow fiber membranes, and hopefully lower the frequency of chemical cleaning, because that's just cost savings all around. It also stabilizes feed water quality into the membrane, ensuring consistent and predictable flux. And it minimizes pressure drop fluctuations, supporting reliable pathogen removal, which is the ultimate goal. All of the above improves the efficiency of your membrane, reduces your operational costs, and helps maintain regulatory compliance for safe drinking water production. As we'll get into, there's pretty strict rules around ultrafiltration or any kind of membrane filtration process. You need to be able to prove that not only when you install a technology, that it continues to meet the standard which it's claiming to meet. As for Rivershore, we rely on 4 different strategies to ensure that all of the above remains true. We have a centrifugal sand separator on our raw water supply line, which basically removes suspended silt, sediment, and colloids even ahead of our chemical dosing and disc filtration system. Next, we have our chemical dosing system. We coagulate with an aluminum chlorohydrate compound, and then follow it with a static mixer to encourage initial particle collisions and agglomeration that you would expect in a coagulation process, and basically to act almost like flocculation, but we do not contain a dedicated flocculation step or a dedicated sedimentation step. So in that way, we are a direct filtration process. Next, and immediately after chemical dosing in the static mixer, we do have our Arcol Amiad 2-inch disc filters, which we'll go into detail in the next couple of slides here. It's worth noting that despite us not having a dedicated sedimentation step, we do have some sedimentation occurring in the tanks themselves. So we remove that accumulated material on a regular basis, depending on the season. During freshet, it feels like I'm constantly vacuuming out these tanks. But right now, and then into the winter months, it starts to get a little less in terms of frequency, but it still occurs at a minimum once per week, because the silt accumulation never does seem to stop on a river source. So that's one challenge that is definitely worth considering if that's you, and I'm sure you've got your own solutions to that problem that I'd love to hear about. So all of the above strategies drastically reduce suspended and colloidal material that will actually make it physically to the membrane filtration step. Settleable silts and material are removed by vacuum pump, like I mentioned. So we actually have a pool brush in our basement next to our sump tanks. So it's a fairly low tech method of removal, but we have not found anything that is more effective. And like I said, removing those settled materials will ultimately save wear, physical wear on the membrane itself. Oops. So as far as the disc filters go, I'll just touch in brief because it is actually a fairly complex process. We rely on our disc filters to remove suspended material that has been agglomerated by the coagulant dose. The way they function is they filter outside in through a stack of channeled disc media, which is compressed by like a spine and top nut in an assembly. So you're holding downward pressure. It relies on forward and back pressure. So back pressure is maintained by a pressure sustaining valve on the outlet side of the collection manifold. In that way, filtration is facilitated, and during the filtration stage, water flows through the inlet and is distributed through the backwash valve. Water passes through filter media. It's allowed to by basically a diaphragm valve. And there's a gallery of 9 individual filters, which you can see in the corner of the slide, that rely on forward pressure supplied by our raw water booster pump, and then also the back pressure provided by that pressure sustaining valve to make sure that the adequate pressure for the media to function is maintained. The backwash valve basically has 2 states, filtration and backflush. During backflush, there's a solenoid that sends a pressure command to the diaphragm valve to enter into a backwash cycle. And then each filter is individually backwashed using the back pressure supplied by the pressure sustaining valve on the outlet. And that way, filters are backwashed, basically using raw water itself at high pressure, and it rotates the media, basically agitating it and shaking away all of the material that's been retained. And then that waste drains to the basement sump. So originally, the raw water storage tank, which these filters supply, was always kind of the dirtiest stage in terms of silt accumulation. But we've found with regular replacement of the disc filter media that we're actually backwashing off a lot more silt into the sump tanks, which somewhat proves that regularly replacing this media instead of just relying on it to get to basically end of life is basically worth it from a treatment perspective and from a cost saving perspective. They do have problems though, definitely. They're made of PVC and those components can weaken over time, especially in such a high pressure system. So the weakening of the PVC components have resulted in basically us operators breaking spine assemblies when we're disassembling the filters for the cleaning. We also notice that the disc media is prone to permanent fouling, the same as a membrane. So submersion and agitation in a mild chemical solution is recommended by the manufacturer on a regular basis. They say every 6 to 8 months, but we're finding that doing it every month or close to every month is having a really good effect on their ability to filter out those materials and not get plugged off with silt. So we've maintained that as a maintenance item. We've also found that maintaining a proper coagulant dose is essential for maintaining the effectiveness of the system, because you're making your soluble organics insoluble in maintaining that proper dose. You can also overdose coagulant, which is an unfortunate situation, and it causes basically the filter to be blinded off in a precipitated chemical residual in the form of like a slime, which makes it impossible to effectively operate the system. So paying close attention to your coagulant dose, like in any process relying on chemical coagulation, is an important part of the process for sure. Now we're getting to the good stuff. We're going to chat a little bit about membrane filtration in general, and a little bit in the next few slides about how Rivershore's process is a little bit different from a typical, I say typical, but there's so many different configurations, it's hard to tell what's typical. But in Rivershore's plant, and basically any plant using UF membrane filtration as the primary mechanism of treatment, the membrane itself does the heavy lifting in terms of pathogen removal, and it provides a standard of treatment far above the pre-treatment steps individually on their own. Specifically, UF membranes treat water for potable use through physical separation, mainly, relying on very fine pore sizes, typically in the 0.01 to 0.1 micrometer range, or 20 nanometers, I think that graphic says on the slide, which the standards range according to which text you're referring to, but generally a very, very fine pore size, more porous than, say, nanofiltration, but less porous than microfiltration. There's a bit of a degree with obviously reverse osmosis and desalination processes being the finest pore size and producing the highest level of treatment. but also requiring the most in terms of energy costs and pumping pressure and all associated parameters. So at that pore size, the ultrafiltration membrane is acting as a robust barrier against suspended solids, bacteria, protozoa, and some of the larger viruses. Particles and microorganisms larger than the membrane pores are physically retained on the outer side of the membrane itself, while high molecular weight organic molecules are partially removed through size exclusion, which also reduces fouling potential and improves the overall clarity of the water going through. In addition to basically the pure sieving action, UF membranes can retain some viruses and colloids via adsorption and other surface interactions, particularly if the membrane surface is hydrophilic or carries charge. In our case, the XF55 modules that we use are hydrophilic, so they do gain us the benefit in this way. Accumulated particles on the individual fibers of the membrane or within their lumens, which is basically the hollow inner channel of a fiber or a tube-shaped membrane element through which liquid can flow, are removed through backwashing with permeate water and, in many systems, air scouring, which restores flux and maintains consistent barrier performance over time. While UF is highly effective at removing pathogens, it does not in any way retain or does not in any way inactivate microorganisms that are too small to be retained. So permeate is usually combined with, well, by law, if you have a surface water source, it must be combined with some disinfection method, such as chlorination or UV disinfection, and that provides an additional barrier in the form of either a residual or inactivation of pathogens for the ultimate treated water product that you're supplying to the distribution system. We'll talk a little bit more about our specific membrane application at Rivershore. They use a proprietary flow concept that Norit and now Pentair refer to as X-flow. And this concept introduces the possibility to operate the UF process in a dead end mode. They developed a novel membrane filtration element using hydrophilic capillary membranes. Like I mentioned, being hydrophilic or carrying a surface charge really encourages the adsorption of viruses and other of the smaller contaminants. So it provides an additional, it's supposed to provide an additional log removal credit. This specific element design is based on an 8-inch construction, which is fairly common in reverse osmosis elements and similar. A standard pressure vessel or a train or a skid is fitted with usually several elements. In our case at Rivershore, we have 10 elements per train and 2 trains, and that gets us to our design flow of 1,000 liters per minute in terms of what we'd like to be sending to the distribution system at any given time during plant production. You can see from the diagram, hopefully, that the structure itself can be fed from one side, but also both sides. You can see the feed arrows coming in on both sides of the element. And that basically allows the membrane to operate in that dead end mode and basically maintains a low pressure drop across the membrane. Obviously, you've got more water coming in, so more water can come out if it's not restricted. So a constant production over the entire length of the vessel can be achieved. Typically, the process is operated at a constant permeate flow, and that's our case as well. We have PID control over the pump, the feed pump flow set point, so that gets pretty granular, but usually we're operating at maximum capacity, especially during this season, to keep up with demand. As with all membranes, the transmembrane pressure will increase over time during the length of your filter run. a periodical backwash using permeate is required to control the increase of transmembrane pressure over that time. So it's typically scheduled. We backwash every 60 minutes, and we'll go into a little bit of what that looks like in a few later slides. So you can see there's a little bit of data on the slide. Depending on the feed water quality and the type of membrane used, the typical flux rate during filtration should be about 70 to 100 liters per meter squared hours, which is how flux is measured. Don't get too hung up on the actual measurement number. And it should be about 10 to 60 minutes of filter run per the manufacturer recommendations. The recommended transmembrane pressure in the module is measured in bars, and typically the manufacturer recommends less than half a bar. So that'd be like less than 7.25, 7.25 psi. It's important to keep the transmembrane pressure low during filtration. A transmembrane pressure above 1 bar, or about 15 psi, is known to cause a permanent irreversible fouling on the membrane surface. So you always want to keep it below that number, and there's a few ways that we typically do that. Obviously, a different membrane element configuration would have different pump requirements. But for us, we have 2 production skids, UFT01 and UFT02, which both contain 10 elements. So each membrane has a total surface area of 55 square meters, apologies. And it is a hollow fiber membrane designed for inside out filtration. Norit Pentair guarantees a permanent quality of SDI, which is your silt density index, of less than 3, turbidity of less than 0.1 NTU, and a good performance with anti-fouling behavior. This is true. We have alarm capabilities set up to alarm us, obviously, but also to shut down plant production should it ever exceed 0.1 NTU in terms of our permeate quality. So that's just another barrier of protection for our treatment system. The element contains the vertical design of inside out technology with the advantage of a minor bleed flow across the membrane surface, which does not result in a dedicated waistline. It just kind of covers the actual inside of the surface. You can see feed on that initial diagram earlier. The bleed flow itself eliminates the need for an external waistline, which are fairly common to other membrane applications, including some of the pressure vessel designs that are common in smaller water systems. So that's another benefit, is obviously if you have a waistline, you have waste, and our goal is to waste as little as possible. So yeah, we'll talk a little bit more about our pump capabilities here. So obviously, in any membrane treatment process, you require a certain amount of forward pressure during treatment to maintain the pressure requirements of the membrane itself. And to provide that forward pressure, we operate basically 3 end suction centrifugal pumps. We have a lead lag standby configuration, so we always have 2 pumps operating at the same time with 1 pump ready to go should one fail on flow or outlet pressure or inlet pressure or any other parameter that the PLC is constantly measuring. For our backwash, instead of a dedicated pump, which is fairly common, we actually use head pressure from the distribution system. The pressure enters into the system at about 80 psi, but is stepped down by a PRV to about 30 psi, which is much more close to the design capabilities of the membranes. As for the transmembrane pressure, the maximum allowable during backwash is 3 bar, or roughly 45 psi. We never exceed this number. Usually once it makes its way, once all the valves are done actuating and stuff, it's about 15 to 20 psi for back pressure, and then obviously a forward flush is occurring at the same time, which we'll get into in the next slide. And in this way, we're basically providing enough flow velocity to remove all of the particulate that's been retained, and it ends up in the backwash tank. Under normal operating conditions, not during backwash, our transmembrane pressure usually sits anywhere from 4 to 6 psi, which is a pretty good number. So most, if not all, membrane processes contain some sort of backwashing step to remove the temporary fouling that accumulates due to exclusion of material on the membrane surface. As you can see, ours is timed to a 60-minute filter run, and you can see the specific steps and the times relatively in which they occur. We start with a 20-second forward flush, and then, or pre-flush, sorry. The sequence starts with that pre-flush, and then all valves close, and then we do have a set of basically forward flush dedicated valves that are normally open during filtration as well, and they initiate flow from that pump. The flow and pressure are then introduced to the system by the opening of MVO2, which basically gives us that pressure, head pressure from the distribution system. And then all valves actuate accordingly to accommodate that pressure and make sure we're not dead ending or causing water hammer. So we do have dedicated drain actuators that dump into that backwash tank. Once both banks are flushed, the system goes into a brief post-flush to remove residual chlorinated water, which was important when we were doing chemically enhanced backwash, which we're going to touch on, but is even more important for that removal. So we're not recycling a chemical residual if we can help it. So yeah, you can see the total sequence on the slide there, as well as which valves turn at which time. So just to touch a little bit on our recycling process, without a recycling process of some kind, these specific membrane elements only have about 70% efficiency just due to the sheer volume of backwash water needed to clean them routinely. So to combat this, Rivershore's design incorporated a backwash water recycling process with a separate 4-element UF pressure vessel, which we call UFTO3 or train 3. During a backwash, basically it receives, a backwash tank receives backwash water from the 2 production trains, flows over into an additional train that acts as basically a equalization step in terms of water storage. And then the train itself filters it as if it was the production process, but the ultimate point is returning that backwash water, once it's been ultra filtered, the same as the production water, back to the front of the process in the raw water storage treatment tank. So in that way, we're actually achieving close to 95 to 97% efficiency in terms of the water that we bring in. Especially as time goes on, not wasting water is going to become even more important part of the process. So the fact that this was incorporated so early on shows that those kinds of things were being considered at the time. There is a different mode that you can operate in and bypass UFTO3 completely, and that way water from the backwash tank and the backwash recycle tank is pumped strictly into the basement sumps, where it is dechlorinated and sent out to the irrigation storage ponds. In that case, we are only achieving that 70% water use, so this is not a mode that we like to operate in on a regular basis if we can help it. And overall, the system helps maximize the recovery while protecting the environment from the excess discharge of chlorinated water, which whenever the UFTO3 is in waste, we also dose sodium thiosulfate as a dechlorination agent to prevent the discharge of chlorinated water. And hopefully by the time it gets to the receiving environment, there's no free chlorine residual at all. And we do measure that whenever there's a risk of that happening. Just a quick note, just because it's common to other processes, we do not have an air scouring method. Obviously, I've talked a bit at length about how the design doesn't incorporate that feature, basically due to its inside-out filtration concept. It allows fouling to be effectively removed just through the backwash alone is the idea. In contrast, something like a Z-Weed ZW1500 is outside in. So submerged fibers accumulate solids on outer surfaces in open water, making air scouring pretty essential to basically physically scrub debris during cleaning. So in that way, it becomes necessary. For us, not so much. So before we get into cleaning, I just wanted to touch a little bit on how the brains of the operation. So the membrane trains all contain many 6-inch butterfly valves, which are controlled by motorized actuators, which permit or prevent flow according to the current status of the production train. During production, valves related to the forward pressure and flow are open, allowing flow to pass through the membrane according to their flow configuration to create permeate. When a backwash is triggered by the PLC, SCADA controls ramp down feed pumps into their back flush flow set points and actuate the valves accordingly to allow the system pressure to be introduced and to backwash the membrane. We are able to adjust our feed flow controls of our pumps basically to provide adequate forward pressure and flow to make sure the action of the filtration is actually occurring. And every set point related to pressure, flow, turbidity, and even differential pressure, like you can see in the slide, are all adjustable by the operator. So it really allows us really fine control over our system and the ability to observe and make adjustments if necessary, but we try to keep things pretty close to what the manufacturer recommends. We're going to get into cleaning a little bit here, and just some brief differences. Obviously, I mentioned that there's no air scour on our membrane modules, so we rely completely on, in our case, regular hydraulic backwashing. And there was a dedicated chemically enhanced backwash system, basically a chlorinated backwash, but they were having trouble maintaining an appropriate hypochlorite dose, given that we were recycling a chlorine residual to the front of the plant. So it was very hectic, haywire. It was tough to keep it stable. So the system was ultimately removed. The initial idea was to dose at about 20 parts per million to basically enhance the removal of the existing backwash. They mention in historical context, because obviously this system was removed before I began operating it, that operational experience would be necessary to balance the cleaning efficiency of the chemical clean with the amount of chlorine ending up in the backwash recycle tank, which is exactly the problem that they ended up having. And it was just too difficult to manage. So the approved solution was basically just to remove it entirely and get to a place where we rely solely on hydraulic back flushing in order to remove that fouling. But that's not to say that we don't have to clean in place, just like all other membrane applications. In terms of us, the chemical CIP occurs as needed to address temporary fouling. Obviously, with a membrane, you're always going to end up with some measure of permanent fouling that accumulates over time. In our case, and just from a bird's eye view, we use a 500 milligram per liter sodium hypochlorite for a base clean and a 3,000 milligram per liter citric acid for a more acidic clean. And they address organic and inorganic fouling respectively. Our membrane fouling seems to be specifically organic in nature, so we find that our base cleans often do most of the heavy lifting in terms of recovery. And we'll talk a little bit more about the things that denote a successful clean in place in the next few slides here. The operator determines the need for a clean in place through a few factors, but most of it is through noticing that your transmembrane pressure is spiking over time. And with an aged membrane, it can depend on what technology you're using, but for Rivershore, we usually do twice a year with a much higher frequency on UF-TO3, just because it's receiving a higher concentration waste stream. Next. And just a little bit about our cleaning process in abstract, because it is fairly complex and we have a whole standard operating procedure, but we do have a freestanding tank, which you might have been able to see in the previous slide. Apologize for the mess. I'm sure that I had other things going on at that moment, but yeah, we fill that tank with bulk chemical solution. So distribution water is filled to a certain point to act as the solution, and the chemical agent is added as the solute. To begin the clean, you have to select a specific membrane skid, so UFTO 1, 2, or 3, and it's a hand valve system, so that basically you go through the procedure and turn them according to basically allowing a recirculation pattern to occur. So you're constantly pumping and reusing the same chemical solution as a cleaning agent. And there is basically a filter, a cartridge filter on the outlet of our recirculation pumps, which trap any particulate that either doesn't settle in the tank or is caught in the turbulence of the recirculation stream. So just a few details. The cleaning solution is typically brought up and recommended to be brought up to about 35 degrees Celsius. This increases the efficacy of the clean. Obviously, it's easier to clean with hot water than cold water, but it also prevents temperature shocking, which can occur if you obviously are just thinking of a scenario where you're using a chemical solution as a cleaning agent that's been brought to the appropriate temperature, but then rinse with water that is 20 degrees cooler, you're actually going to cause some shrinking and expansion of the membrane fiber, which can cause damage in and of itself. So it's important to rinse and clean with temperature consistent water. You might also have to adjust your pH. A base clean is much more effective at a higher pH, usually around 10.5 to 11. So you can use agents like caustic soda or lime or whatever you would use to adjust pH in a treatment process to do the same here. Normally, our citric acid dose is enough to reduce the pH enough into the desired range, which is usually around 3.2 during the cleaning process. When you get to those low pH numbers, say if you were dosing hydrochloric acid or something to get the pH down low enough where you needed it to be, which is not uncommon, it can actually damage pH meters. I find the lower that you go in pH, the more likely damage to your meter is going to occur. So I just pulled these out of our standard operating procedure. You want to do a solution calculation to get to your target dose based on the volume of your chemical solution. I'm not going to actually bore you with the math, but it's your typical C1 V1 equals C2 V2. We've appropriated into a more of a shorthand here. So on the top, you can see our chemical solution calculations. On the middle, you can see the conversion from US gallons to cubic meters for the purposes of the volumetric calculation. And on the bottom, you can see the basic form of our standard operating procedure. Yeah, so it's basically the same for both your base clean and your acid clean. And that's the idea. You're doing your clean into a vessel that's been depressurized and drained. You're allowing it to soak and make contact with the chemical and physical constituents that it's trying to remove. You drain, and then you rinse. And then after you're done, you have to have a way of measuring whether it was successful or not. The first and probably most important metric is your transmembrane pressure. As you know by now, the fouling on the membrane causes that pressure to rise. So one of the things we check first is whether it drops back down to or close to its baseline after the CIP. A nice clear reduction here is a strong indicator that the fouling layer has been removed and you're back to basically a clean membrane. Next, we look at the recovery or the permeate flux. So basically this tells us how much water the membranes can produce for a given feed pressure. If the recovery goes up after a clean, that's a clear sign that the membranes are freer flowing and operating efficiently once again. Another operational check is backwash frequency. Fouled membranes require more frequent backwashing to maintain the same flow. After a chemical clean in place, we should see that backwashes are less frequent, or the volume of backwash water needed drops, but more so on the frequency end of things. What you can also look for is your water quality parameters. So turbidity is an obvious one. The permeate should come out crystal clear according to the design specifications of your membrane. The silt density index is another one to look at. Some plants will also look at your total organic carbon or organic content through UVT measurement to see whether organics were effectively removed, especially if organic fouling is the main issue like it is with us. And there's some other minor ones. Basically, we covered the important ones. There is also just using your operational and visual checks are, especially if you have a way to actually visually inspect the flow, like a clear sight glass or something like that, or a transparent pipe on the permeate collection tube. Is there any unusual pressure behavior? Is there bubbling? That kind of thing. So I just went into a little bit about how you may need to treat the waste stream from your chemical clean in place. Obviously, it has to be treated well and according to legislation in British Columbia in order to be discharged to an environment. And there's a few challenges listed on this slide as well. So first, every time you clean a membrane with a chemical CIP, there's going to be a degree of degradation, permanent fouling, we refer to it as. Every time you CIP, you're going to be using a certain volume of chemicals, so that needs to be accounted for in your chemical budget. The waste stream is what I meant by chemical disposal. So you're dechlorinating or doing whatever you need to do in terms of pH adjustment to get it back up to the parameters where it's acceptable to discharge to the environment. And yeah, you can even do integrity testing immediately prior or post to the CIP in order to, if you're doing it to address some integrity issue, which we're going to discuss in the next couple of slides here. Yeah, this is basically just some strategies that can be used to, before discharging. It's mostly just for information, so you can always go back and review it after if this is relevant to you. And same thing with these numbers. This is basically where your number should be at prior to discharging to your environment, but these things can change, so it's always best to discuss with a regulator what your actual goals should be according to your permit as well. So we're going to just talk about membrane integrity a little bit. Of course, in a real world operation, membranes don't fail all at once. They typically degrade slowly. So what we do is prove membrane integrity through integrity testing, which occurs on a daily basis per regulation. It's really about just managing risks and proving that your membranes are treating to the same degree that they were when they were installed. These are the references for what one should be referring to when it comes to your membrane integrity. So it's important in general to know some of these, not by heart, but to be aware of the ones that are relevant to your facility. These are the common methods. I'm only really going to touch on the first three just because they're the most common. Bubble points, you're wetting the membrane, applying air, and seeing at what pressure bubbles start to appear. If air passes through at a lower than expected pressure, it tells us there's a hole or a breach. This is what we do at Rivershore. If we do detect a breach through our air diffusion test, we'll actually pull it, submerge it in a bath, and do basically a bubble point test to locate the damaged fiber and stick it with a pin. The next common is a pressure holder pressure decay test. So this is a little bit more accurate than a bubble point test. And it's a favorite for routine integrity checks. You can see a little bit of information through there, but you pressurize the membrane, isolate it, and monitor how much pressure drops over time is the idea. And the third is forward flow or air diffusion test. This is what we use. It's a variation of the bubble point tests and involves passing air through a wetted module and monitoring the flow. It's simple, inexpensive, and it works well for checking individual modules. Downside is that it mainly detects larger defects. It won't usually catch very small or partial fouling related breaches, but it's generally considered useful for localized checks, daily checks. So yeah, we use an AIT, which is a membrane integrity test, basically introduced by NORAD, and it's basically an air diffusion test or a gas diffusion test. And you can kind of see what the relative process is, where draining the production side of the membrane, pressurizing it with air, venting the permeate side, stabilizing it for a period of 480 seconds, and measuring that flow. And then once that measuring period has taken place and we've proven there is no flow across the pressurized membrane, the test is considered a pass and moves on. And like I said, if we had a fail, we would pull it out of service, or we can even isolate it and continue in production. And then we would do a bubble point test, locate the damaged fiber, and do our repair in-house. So yeah, basically the goal of membrane integrity testing is to ensure that each unit is functioning properly, help to determine when to end your filter runs operationally, and to detect any short-term or rapid increases in turbidity that represent a process failure or potential risk to the treated water. You can kind of see all the important parts of measuring the permeate water quality, and the things that we use are basically laser analyzing the turbidity, and we're also measuring UVT and distribution as a daily practice in our in-house labs. And we do have that alarm state incorporated, where if it goes over 0.1 NTU, it alarms out the plant, immediately issues a warning to the operator, and will not produce water again until the issue is addressed. So, I mean, to finish us up here, I just wanted to talk about, because I think we're just about to go over time, we'll talk about a few operational challenges we've had at Rivershore related to the ultrafiltration. Obviously, it's a membrane and it needs to be replaced at a certain schedule. It's pretty predictable, but the 10 to 15 year life cycle is pretty typical. So you need to be able to budget logistics and cooperate with interior health and other regulators to basically make sure that it's completed, replacement is completed under a construction permit. I mentioned the efficiency problem and the fact that it doesn't remove viruses, so it requires an additional disinfection step. Chlorine analyzer issues. Yeah, so whenever we backwash, we do get a large surge of chlorinated water, which throws off the PID dosing a little bit, but typically it corrects itself. We initially didn't have a PRV on the backwash line, so it would blow apart end caps and all kind of cause pressure related issues and destroy membranes even. I mentioned the chlorinated backwash cycle, and it basically spiking free chlorine residual in the raw tank. Yeah, and these are a little less relevant, but there may be problems related to pumping costs if one were to choose these XF55 modules over others. You can't really have a way of visually inspecting them either, which has been an operational challenge. So you basically just have to clean it and hope that it's clean based on the key metrics that I measured earlier. So you're not completely guessing, but they're highly sensitive in terms of their feed water quality. So you don't want high silt and algae, which can cause more frequent backwashes and chemical cleans. It's pretty crucial to have a pre-treatment step, as I mentioned. And they aren't compatible with all oxidants. And it's usually your acid clean that'll cause that permanent fouling. In the context of a small water system, especially if you're on groundwater, these might not be the best main treatment mechanism, just because you have that iron manganese hardness and other things to worry about. So chemical oxidation and stuff becomes necessary. On a high natural organic matter source, that might be a problem as well if you didn't have some kind of pre-treatment. With membranes, you always have a burden of integrity testing on a daily basis. So it requires daily operation or automation, which is preferred. And it removes turbidity, bacteria, protozoa, and some viruses, but things like dissolved salts, dissolved heavy metals, pesticides, molecular weight, low molecular weight organics and stuff will require additional treatment steps like disinfection, granular activated carbon filters, or reverse osmosis. Sometimes UF is used as pretreatment for reverse osmosis. Mention the capital and replacement costs. This 5 to 7 year is not correct. It's usually 10 to 15, depending on your source water quality, of course. And you need to be able to manage the UF membranes from an operator experience perspective, kind of know your system, run your system so your system doesn't run you. Yeah, and we've dealt with a few challenges as well. The plant was originally intended to run itself and just have an operator be able to walk in, fill the chemicals in the morning and walk away and not have to worry too much about it. Anyone with any experience in these types of processes knows that never goes the way people think it's going to go. So in 2016, Rivershore hired a utility contracting company to manage the system and all other utility systems, while Gulf Ops was able to focus on the Gulf operations side of the business. And from 2016 to 2022, that was true. From 2022 onwards, I was hired once the contract lapsed, and now we're finding it a lot more simple to basically get Strata Council to cooperate with necessary spending, because when you have a public infrastructure like this, spending is required, and you can either do it proactively or reactively, and one is definitely easier than the other. But now we retain a operations consultant, comes by once a week. He's probably watching this. So we have stronger in-house expertise, more control, and better long-term resilience on the system. Just a few mechanical problems related to actuators. They require adaptation to the butterfly valves, and those kits became unavailable. So we've had to kind of custom make a solution, and we still don't have the supply side of that completely handled. We're running into PLC programming limitations that existed in 2011 and continue to exist even in 2025. So we're slowly working with an instrumentation tech to kind of get these issues worked out as they come up, and components of the PLC systems are failing as well. So it's just a constant battle to keep up with these things, I find. And I already mentioned the intake sump sediment removal. You can see this was once the work was complete, but we were hydrovacing out silt that had accumulated inside the structure. And our hydrovac operator said that we were actually able to remove more than a ton of accumulated silt. So it's just one of the things to consider on a river source. If you can take advantages of low water periods like this, that's majorly to your benefit. There was a UV disinfection system that was deemed redundant, so it was removed. So now we rely on sodium hypochlorite as our primary disinfectant and a free chlorine residual in our distribution network as secondary disinfectant. We are able to do that because the distribution system is completely looped. In a lot of cases, interior health is not going to go for this. But they made an exception for us just because we were able to prove the quality and the maintenance of a free chlorine residual at all parts of our distribution system, which is important. We have no dead ends. So yeah, no real accumulation of organics or biofilms or scaling or anything like that. And obviously our membranes were aged, and trains 1 and 2 were replaced in 2021 and 2022, which was a significant capital cost. There was about $3,200 per element, 20 elements. The math adds up pretty quick. And I was actually able to replace these specific elements on train 3 as well in 2024. So now that everything's fully replaced, we shouldn't have to worry about it until 2031, but it seems like it's coming up rather quickly. So I think that is it, actually. Yeah. So there's just a few things that you can reference if you're looking through the slides later. Yeah, I just basically put some of the more basic references down. for your convenience. And I know I bit into the question period time a little bit, so I appreciate you bearing with me. It was an honor to present. And thanks again to the BC Small Water Online's Help Center, and thanks to you so much for attending. If there are any questions, please post them in the live chat and we will definitely get to them.
Thanks, Brad. That was great. So much detail. Rob, are you online to do the Q&A? Maybe not. Okay, well, we'll start. We have one question that came in. I will just post it here. Is XF55 valid for saltwater systems?
In this case, if the primary goal would be the removal of like a desalination kind of process, it wouldn't be valid, no. You would need to look into reverse osmosis, unfortunately, just because strictly due to the fact that it's a dissolved particle, and the pore size of the UF would just basically not be enough to remove it through physical or chemical means. So,
thanks. Are your 200 connections metered?
No, I wish they were. It's a significant upfront cost for us. We do have a few quotes and ideas kicking around, but there isn't a ton of interest on the consumer side either. If they were metered, I'm sure there would be more pressure for the separation of residential irrigation from domestic treated water, just due to straight up costs. But no, at this point, we are not metered, and the cost prohibitiveness of installing meters is unfortunately kind of making it a non-option at this point, unless it's a regulatory requirement.
Excellent, thank you. Another question, what is the cost and complexity trade-off between regular integrity testing versus the removed UV treatment?
It's a really good question. The regular integrity testing is a requirement in British Columbia. It would be kind of unique to your filtration setup, basically the methods. And some of them have even LRV values attached to the test results. And Interior Health really loves to see numbers attached to these results. For us, we basically had to develop our own system to prove, that our integrity is not trending downwards. It didn't really come into play when it came to the UV removal, just because we were able to prove again our free chlorine disinfection residual, but additionally, just due to our continuous monitoring of turbidity on the permeate side, they were able to make the judgment call that the UVs were no longer necessary. But there isn't really a system where you're treating potable water and not able to do integrity testing, or not being required to do integrity testing, I should say.
Thank you. What is your peak daily demand in meters cubed per day?
Yeah, that's another really good question. At 200 connections, it depends on the time of year. In January, I've seen it as low as 55 to 60 cubic meters per day. At which point the plant is only producing water, I would say, for like an hour a day. At the end of August, during our hottest period, I've seen it as high as 1,100 cubic meters per day. In which case the plant is running close to 20 to 22 hours per day. So it can really range based on the time of year.
Thank you. That is a big range. Greg asks, what is the laser turbidity meter you mentioned?
Yeah, so for us, we're still using the originally installed, their HAC or Hawk, however you pronounce it. They're the laser turbidity meter. I think they're they're 660 SCs, and they perform extremely well. We have them calibrated annually, so that it takes some of the maintenance off our backs, and like I said, they're highly accurate. We haven't had any problems.
That's great. Stefania wants to know what the size of the population that your system serves.
Right, so we do have 200 homes on the connection. It's tough to say because it doesn't really incorporate us into census data. We're just part of region L or something. So we can assume it's a mostly retirement community. So there's probably like 2 to 3 individuals per household. It used to be that we had more snowbirds, so the demand would naturally drop way down when everyone went south. That's no longer the case. We're actually seeing a lot more young families move in. So we can kind of track our increase in demand that way as well, in addition to the 2 commercial buildings.
What do you have for backup electrical power?
That's a good question. At the moment, we don't have any, which is something that we're hoping to tackle next year. Just because in the event of even something like a wildfire that, prevents electrical transmission from making it over to our side, we wouldn't have a ton of options. Depending on the time of year, we would only have a day or so before we ran out of treated water, in which case we would have a few options. You could truck water in, which is not ideal, or we do have a deal set up with a rental establishment in town where an emergency generator could be provided, and they kind of know the situations in which that we would require it, and we know them personally, so we could skip to the front of the line potentially if it affected a wide area, because there's a lot of ranch land around too that would be after, the same application.
What is your target free chlorine residual at the consumer endpoint?
Typically, I run it a little bit higher than most operators would, given that we do not have an additional disinfection step. So I typically try to target 0.1 to 1.0 or 0.8 to 1.0 parts per million leaving the plant. And then usually once it gets to the consumer tap, it's usually about 0.6 to 0.7.
What is the max TSS of your feed water supply, and what level do you drop it to prior to the UF skid?
Another good question. We don't measure total suspended solids of our raw water. We typically go by NTU and UVT alone. So typically on a non-freshet season, our NTU is actually anywhere from like 1 to 3 NTU. Like I was saying, the South Thompson is an amazing water source, so we're typically not dealing with too many problems there. We do measure UVT or UV transmittance for the soluble organic portion of the raw flow. So coming in, it's usually anywhere from 85 to 90, usually on the kind of middle of that, so like 88. And by the time it gets to the UF skid, I like to see turbidity reduced below 1, usually like to 0.7, and UVT at around 91. And then by the finished water, we usually have 96 to 97 UVT.
Cool, thank you. I just wanted to take a moment to say we will be posting the presentation and video to our website in the next few days. So if you have questions about that. Another question, Catherine asked, given your location in the South Thompson River, can you speak to practices in place to protect the environment and fish populations, screened intake, position of intake, and chemical management?
Right, well, that's an excellent question. I'll kind of tackle those things in order. So we do have screened intake. It's obviously it's below the level of the river and it's a buried structure. But given BC legislative requirements, we do have fish screens to prevent impingement. It kind of acts as a bit of a grate, even though no fish would realistically be able to access those points. It's still just another level of security, and like I said, a legislative requirement. The position of the intake is important. It's about, I believe, 150 meters from the shoreline on the south side of the river, basically facing a deep channel. So that way we're not getting a ton of surface debris and stuff coming in during the high flow, high level periods like freshet. The chemical management side of things is only really a concern after a CIP, when we have basically a waste, a high strength waste stream, in which case we do the pH adjustment, we dechlorinate appropriately, and we're measuring the whole time. If we're discharging to the environment, it's a separate pump that's running, a separate chemical dosing pump that's running. I would have loved to get into this, but obviously we only have an hour. So basically I'm trying to meet a certain standard of pH adjustment and chlorine residual removal And once I'm there, then it's safe to run those pumps.
Great, thank you.
Mhm.
What is the annual cost for each of the 200 connections?
Right. The utility fee is basically aggregated with other domestic kind of fees into a strata fee. I'm unaware of what the actual cost is per month, but I think last time I remember it being like between $250 or $300 per consumer residence. They're getting a hugely good deal on it. And as such, my operating budget is not substantial outside of capital improvement projects. It's something that I have to manage fairly carefully from month to month.
Nice, thank you. What is the hardness of the water for inflow for the plant?
Mm-hmm. It's a typical surface river water source. So we don't actually measure for hardness just because it's not a parameter that we're worried about specifically. If you had a groundwater source, this would be way more relevant and probably one of the major things you're worried about. But measured, your total hardness is usually between 35 and 47 milligrams per liter. And alkalinity is fairly similar. So we were originally coagulating with ferric chloride, and as anyone with that coagulant knows, it consumes alkalinity at an incredible rate. So it just wasn't performing its function. So in that way, alkalinity and hardness are relevant still to the surface water source, just because alkalinity is so crucial for coagulant dosing.
That's great, thank you. Do you require a permit from MOE or DFO to drive the back truck out on the riverbed? Yeah.
Yeah, it was a hugely involved process. We involved MOE and DFO. We required continuous turbidity monitoring from environmental, the word is escaping me, but we basically used an engineering firm to handle that side of things for us, the regulatory compliance, just to make sure our T's were crossed and our I's were dotted. We also fully cooperated with KIB and let them know what our plans were directly to the council. So they were aware as well, but that still didn't stop us from getting reported. Obviously, we're majorly visible both from the golf course and from the highway side, so people definitely had their concerns, and rightly so, because around the intake area is actually a salmon spawning area, so it was quite crucial that excess turbidity and stuff didn't end up in that area, and it didn't. Yeah, great question.
Great, thank you. That's great. I think that's all the questions. Thank you for a fabulous presentation.
Thank you.
Thanks for all the great questions and answers. Always a nice conversation going on. Just a reminder to attendees that your certificates will be sent out to you tomorrow afternoon to the email address that you used to attend this webinar. I will post the presentation and video within a day or two to our website. And if you have any other questions for ourselves or for Bradley, just send them to the info@smallwatersystemsbc.ca and we will get your questions to the appropriate person. Yes, and don't forget to attend our next webinar on November 18th. We will be doing disinfection byproducts. So that promises to be there's always a great topic. So thank you again, Bradley, for your great presentation and for sharing all your knowledge. And thank you for everyone for your patience with our technical difficulties and for attending today.
Thanks so much.
Okay, bye.